Good morning to everybody. As Eno said, I'm one of the Nahuel presenting here. I'm Nahuel Riva. I'm from Argentina. I work for Qthe, which is a French security company. Basically, I'm here to talk about Philips TriMedia, which is a not well-known architecture, an old architecture, but you can still find these CPUs on the market in some old devices. I thought that this talk could be interesting for you because there is a lack of information about this architecture, and it is interesting to see what's about it. This is more or less the agenda. The talk is divided into two main parts. The first part is about the analysis of the device. I found this architecture. In this part, I'll try to show you chronologically which were the steps I followed to try to get access to the camera. And on the second part, we are going to see the architecture itself. This is a small introduction about me. Now I work for Qthe on the embedded team. Previously, I worked at Core Security doing exploit development. Before that, when I was a teenager, I liked to break software protections. Well, I like a lot of stuff, mostly those things: reverse engineering, InfoSec, asado, which is the Argentinian barbecue, beer, tattoos, etc. Okay, this research started last year. Basically, some years ago, with a former coworker, we did a presentation at Hacklu in Luxembourg about how to hack different models and brands of IP cameras. Basically, we found a lot of vulnerabilities in these cameras, remote vulnerabilities, remote code execution, and we could hack all of them. And the interesting thing about these cameras were that all of them were ARM or MIPS-based cameras. Since then, I was collecting a lot of cameras, different models and brands, and all of the cameras also have ARM and MIPS. But last year, I bought one, the Link camera, that was different to all the others I found in the past, and that's the camera that has the TriMedia CPU. As I said previously, there isn't too much information available on the internet about TriMedia. There are a few resources. The main resource I found was that blog, which is not available anymore, but you can use a web archive to read if you want. And starting with this research, I just published 2 blog posts before this talk. Third one is coming in the next couple of days, also about TriMedia. You can find a more detailed information on those blog post series than in 1 hour here. Okay, the first part is about the analysis of the device. This is the camera, the IP camera. All those features are the most common features you can find on the cameras you can buy today. This one in particular has pan-tilt zoom, motion detection, remote control, Wi-Fi, etc. The first thing I do when I have an IP camera is to start with the firmware analysis. In this case, I use Bingwalk to do a quick firmware analysis. And as you can see on the screenshot, Bingwalk was able to identify a lot of HTML and pictures and web things, but there is no trace of kernel, bootloader, or the file system. When you deal with IP cameras, you have like 2 types of firmware images. The first one is the system firmware image that contains kernel, bootloader, and the file system. And then you have the web firmware that has all this stuff. But this wasn't the case. There were only one image available, so everything has to be inside this image. But at least for Bingwag, there isn't any bootloader or kernel image here. So the thing is that I started with that version, which is the one available on the camera. But then I realized that there is a part of the firmware image, especially the first megabyte of data, that Bingwag was not capable to recognize anything. So that was weird. So I used the entropy analysis of Bingwag to try to identify something. And as you can see, the first megabyte has high entropy. And that may be indicating that either the firmware image is compressed or encrypted. And at the end, we will see that it's compressed. But at that time, at the beginning, I couldn't identify any compression algorithm or any known cipher. So I was dealing with a not very common firmware image. As the firmware analysis didn't throw any good results for me, I tried another thing, a more dynamic approach. I tried to identify all the running services on the camera to try to compromise any of them and get access to the camera. The first three services you can see there, which are the HTTP, FTP, and Telnet server, are the most common services you can find on an IP camera. And then there were other three services that were a little weird for me. I started by analyzing the Telnet server. This is a custom Telnet service with some commands you can see on the screenshot to dump some information about the MAC address, IP address, DNS servers, etc. To clear the screen, whatever. But commonly, you can also find in this type of services running on the camera a shell that gives you access to the file system. But it wasn't this case. So I tried to do a more deep analysis on the firmware and found some other undocumented commands which are not very interesting. There were two that I guess they were related to turn on and turn off any fan inside the camera, but I couldn't find any. The new web to create a new root folder for the web server, and the suicide, which is used to restore the camera. Then I went for the FTP server analysis. This FTP server only allows you to be on one root folder. You can go away from there. And this web server has three main files there. The most interesting one is the flash.bin, which is the entire file system. But unfortunately, I wasn't able to dump it. It has only write permissions. I couldn't extract it from the camera. Then you have the system log, which has all the activity of the camera, and the config.ini file, which is it contains all the configuration of the camera. I could read that file. It has all the credentials for the web administration panel. This is the web administration panel. It has default credentials, also a guest account in which you can see some screenshot taken by the camera, but it's not enabled by default. That's unfortunately not good for an attacker. And one interesting thing about the HTTP server is that it's the same available on Vivotech IP cameras. So I started by looking at the CGI applications they have, because there were some vulnerabilities in the past affecting this web server. But in the case of the TriMedia camera, in order to access these CGIs, you need to be authenticated. So it wasn't interesting neither for me. And finally, these are the three other services running on the camera: the radio through Ethernet, which is used to broadcast audio data; the FileMaker service used to stream video; and the complex link, which is used to synchronize audio and video from the camera. As at that point, I couldn't compromise any of the services running on the camera. The firmware analysis didn't go any way also. And so I tried another way, which was to open the camera and to see what's inside. At that point, I realized that I was dealing with a very uncommon hardware. I found two PCBs inside the camera. The main PCB has all the main components: the CPU, RAM, flash, and the other one has all the functionality for the pan tilt zoom feature. So the CPU available on this camera was the Philips TriMedia PNX1300. It's a 32-bit processor. It has 128 megabytes of RAM, 16 megabytes of flash, and Wi-Fi, EEPROM, etc. This is the first PCB, the main PCB. On your left, you can see all the Wi-Fi, flash, EEPROM, etc. And on the back of the PCB, you can see the TriMedia CPU. This is the second PCB. And also I found two pinouts. The one marked in red has 10 pins, and the other one has 12. So at that point, I thought that it would be interesting to try to identify which those pins are in order to get physical access to the camera. Because I found on the datasheet of the PNX CPU that in the chapter 18 you have the JTAG functional specification, in which mentioned that you have a JTAG interface to interact with the camera. But it seems that Philips has a proprietary cable to interact with this interface. And there were also other vendor, the Monument Data System, that also have this PCI debugger, but are really, really expensive and are not available anymore. So the first thing I tried was to see which of the pinouts are more close to the CPU. The red ones were a little bit far, so the most interesting one was the yellow one, because there were some traces going to the CPU. So basically, I thought that would be the correct ones. And the first thing I tried was using a voltmeter, but it was the best idea. Anyway, I could get this poor information from that, but of course, nothing worked as expected. I couldn't interact with the interface in any way. So the right thing to do is to use an oscilloscope, but I didn't have one at that time. In fact, it may sound funny, but from where I am, a small city, it's really difficult to find this equipment in a store. We don't have a store for this kind of devices. You can buy one from the internet, but the custom in Argentina is really, really slow. So I was screwed at the time. But I had some Arduinos, and I found that it's possible to build a kind of oscilloscope with an Arduino, but the sampling rate isn't good. It's almost the same as the voltmeter, so it wasn't useful at that time. So I was a little bit stuck at this point. I didn't know what else to do with this device. So I started to look at the CPU itself to see if I could find any good thing that allowed me to continue with the previous steps I was doing, and finally to get inside the camera. So this is just some information about the TriMedia. It was originally made by Philips. Then it was known as Nexperia. It seems that it was used for automotive and mobile devices in the past. Now it's all ARM-based, but it seems that it was used for that. Mostly for the multimedia parts, for video and audio processing. And this type of CPUs are known as very long instruction word. That means you can execute multiple operations at the same time. In the case of TriMedia, you can have up to 5 operations at the same time, but there are others that allows you to have like 8 operations at the same time. And this processor in particular has 128 32-bit general purpose registers. There was an effort to create a 64-bit of this CPU, but it was left. In 2010, TriMedia was shut down, so you can find new devices with this architecture. And Qualcomm tried to acquire Nexperia, but at the end they didn't. This architecture or CPU runs an operating system known as PSOS. It's a real-time operating system. There were some efforts also to port the Linux kernel, the old Linux kernel, to TriMedia. But the project is a little bit old and didn't continue. If you want to program for these chips, you have to buy the official SDK made by Philips, and you write code on C++ and TriMedia assembler. We are going to see a little bit later. And the SDK is only available for big companies, not for amateurs or individuals, like the Link or any other big vendor that wants to write code for this architecture. I found that there are some TriMedia compliant SDK on the internet offered by, for example, the streaming network, but it's a little bit expensive for an amateur, like $5,000. So it was out of my scope. And there are some other options on eBay if you want to try, but there is no SDK available, so it will be a little bit hard to program for that. Anything surrounded by TriMedia is a little bit obscure. No one wants to talk about TriMedia. I don't know why. And there are a lot of NDA contracts signed out there. So the good and official documentation about Philips TriMedia, it's private. However, I was able to find some data sheets and patents on the internet that I used for this research. Also, I already mentioned in that blog. And regarding tools, you have just a few to work with TriMedia. A guy in 2007 wrote a TriMedia disassembler for newer TriMedia chips, the TM32 series, which is a little bit, it's not equal to the one I'm presenting here, but it's similar. Either disassembler has support or had support for TriMedia CPU, starting in version 4, but you have to ask them to give you the processor module, and right now it's not available anymore. In fact, I asked for the module and they didn't give me. So I think there are some NDA contracts there also. So I started a little GitHub to put all the information I was collecting in the past and right now. So if you want to take a look, go ahead. Well, regarding this, the CPU in this camera, as I said, it's a very long instruction word processor. There are others like the Shark and the C6000 that have more than 5 issue slot. An issue slot, if I didn't mention it before, it's like a box inside the chip that has a predefined functionality. So we're going to see this a little bit later. Well, this has a 32-bit register, 128 32-bit registers. The interesting thing about this type of CPUs is that they implement a special instruction for multimedia functions. This is a diagram of the CPU. And regarding the register model, you have from R0 to R127 register. There are two registers, the R0 and R1, that are used as Boolean. You can change the value of these registers. Of course, there is a program counter and 4 special registers, the program control and status, destination program counter, source program counter, and the C count register. The PC SW is used as E flag register, like the ones in Intel 32 and 16.4. The DPC and SPC are used for exception handling also, and the C count just count the clock cycles. The weird thing about this architecture is that you can change the byte ordering on the fly. You have like 5 issue slots, and you can change the byte ordering on each of them. So you have like little endian and big endian at the same time in different parts of the CPU. This is like, I don't know, weird. And the way they do this is by writing that flag, the BSX flag, to the PC SW register. So it's weird. Regarding the memory, there are four regions of memory. The memory hole, which is 266 bytes. The DRAM with 64 megabytes. MMIO, 2 megabytes, and all the rest is PCI. This is not very interesting. This is the diagram of these memory regions. And regarding the TriMedia assembler and the instruction set, this paragraph describes very well what you will find if you start to look at the assembler. It's like black magic, really. This is just an example of the assembler. On the screenshot, you see the output of the TriMedia disassembler. There are some additional information, but you can see all the mnemonics here, which you can guess what they do. And the thing is that these operations inside the instruction may have different, of course, different size. So the instruction size of an instruction will change. And as you can see, this is not really easy to understand, especially if you have like 100 or 1,000 of instructions. It's really difficult to get the code flow. One important thing about the assembler is that an operation is not the same as an instruction. An instruction may have up to 5 operations inside. Of course, they have mathematical operation, logical, branch, and the multimedia dedicated instructions. All the operations are executed in parallel, and each operation has a dedicated space on the chip to be executed. If you pay attention to the previous slide, all the operations inside the instruction can be guarded. That means that the operation will be executed depending on the value of a register. For example, in the last sentence, you have that if R23 is set to 1, which is true, then the R13 register will hold the result from the addition of R14 and R10. This is very easy. Any of the registers in the CPU can be guarded, except for the ones that have a special use. Well, regarding the addressing, you can load and store data using, for example, indexed register plus a value, constant value, or addition of 2 indexed register, or an indexed register plus a scalar indexed with a index. This is not very interesting, anyway. This is the most important part about the TriMedia assembler, which is the compression scheme used by Philips. When you compile TriMedia code, this code is compressed on a byte stream, and then it's decompressed by the compressing unit. The thing is, as all the information is compressed, you have a lot of bit fields that gives you information about the instruction and the operations inside the instruction. So you have to understand all the compression process in order to disassemble an instruction. Well, this is some considerations for the compression scheme. The length of an instruction will vary depending on the size of the operations inside. The operations size can be 26, 34, and 42 bits only. Can be guarded or unguarded, may have 0, 1, or 2 operands, may have some result or not, immediate parameters. And the important thing here is that all operations are compressed except for the branch operation that has a special meaning for the TriMedia assembler. It's used mainly to indicate the start of a function. We will see later about this. And as I said, TriMedia use something called format bits to give information about each operation inside the instruction. These are 2 bits that are located before each operation. And as you have like 5 operations per instruction, you will have like 10 format bits. This is the table with the information about all the possible combinations. For example, if you have all the 2 bits set, which is the 4 case there, that means that you don't have any operation in that slot. So basically you have an op operation. But if you have both bits in 0, that means you have a 26 bit operation with no extension byte. The extension byte is additional information added to the instruction that is used to build the second group of instruction in the second group of operations, sorry, in the instruction. Because what Philips did in order to build the full instruction, they used 2 groups of operations. The first group is built with only 3 operations inside, and if you have, or if you want more operations, up to 5, you have to add more data to the instruction. So basically, they add more format bits and an extension byte. Well, this is what I was talking about. You have 26, 34, and 42 bits. The 26-bit operations are split in 2-bit part and 24-bit part. The 34 are in 2-bit part, 24 bits, and 1 byte extension. And the last one in 2-bit is divided into 2-bit part, 24-bit part, and 2 byte extensions. This is a little graphic to show you how this is built. You have basically, you start with a branch which is uncompressed always, and then you have the format bytes or the format bits for the next instruction. This is a little example. This slide and this one. We have in this slide we have like 4 instructions. For example, in the first one, you have nothing. You just format bits that indicate that you don't have any operation, so it's an op. But for example, on the last one, you have the format bits for the 3 operations you have there with 24 bit parts, and up to this part, it's the first group of operations in instruction. But then, if you want to add a 4th or a 5th operation to the instruction, you need to add, for example, on the first one, you need to add more format bits for the 2 operations you have there, and the extension bytes for each of these operations. And well, this is about the branch operation I was talking about. It's mostly used to create what is called decision trees, which is a given number of instructions. When you find a decision tree opcode, you know that it starts a function, and you continue decompressing the instructions and the operation until you find another branch or T3 bytes, which are indicated with those opcodes, the AA02. And there are basically 4 steps to decompress or disassemble a TriMedia instruction. The first one is to get the instruction length, which is very easy because you just add all the sizes of the operations inside. The operation size is given by the format bits, and the complex mechanism is the unpack and the decode operation. I will not go through all of this because it's really a mess, but this is going to be detailed on the post I'm going to publish in a couple of days. So when after going through all of this process and steps of analyzing the firmware reading about TriMedia, all the architecture, all the details, I wanted to know what was inside of that first megabyte of data I was talking about at the beginning. So I just tried to see what happened if I test the disassembler with those bytes, and magically I found this. All of the bytes for that from that megabyte of data were successfully disassembled in TriMedia code. I found some incoherence in the in the disassembly process, there are some things that don't match with what I reading on the specs. But anyway, mostly all the instruction operations are valid. But anyway, it's a little bit hard to get the code flow from this from this output. You don't know exactly where your code goes, so it's not very easy to get all the idea of what the code is doing. So it's like magic. Knowing that, I started my own project to create an IDA free and open IDA processor module for TriMedia. I'm still working on it. Basically, I don't have all the resources to do the test and to write it in the right way. I had only the camera. Before coming to Troopers, I received some other TriMedia based hardware, so I expect to continue working on this tool. More documentation, of course, is needed for this architecture, and also more affordable tools, software and hardware for amateurs, because this is like it's a mess, and you need special tools to work. And I think this is my opinion, of course. Philips tried to give I don't know, maybe security by security, because the lack of information it's incredible. So anyway, I enjoyed a lot of doing this research. I learned a lot. Well, I think I will continue working with this architect. So that's pretty much all for me.